Stereo view.
So, thank you all for coming to this colloquium. Thank you also, David, for joining us today, for being here, and despite the horrible weather, hopefully enjoying the city of Gdańsk a bit. So, yeah, to briefly introduce our speaker, David will be talking about the near-infrared's basically successor to Gaia. It's currently being proposed, hopefully to be running some years in the future by ESA. David has had a very long, I think, and interesting career. He started off doing a PhD in computational physics in the physics department of Trinity College in Dublin, then moved to Messina and actually spent time in industry working on the maximum Newton and integral missions. Then spent actually some time in Vienna. So he's familiar with Austria. Went back to industry as a space system engineer for the Herschel and Planck missions, and then switched to the Department of Astronomy and Theoretical Physics of Lund University, where he's been working for quite a few years now on a large number of space missions, including very significantly the actual Gaia, which is no longer the ongoing Gaia mission, because it shut down, I think, 2 weeks ago.
Yes.
So yeah, with that, let's talk about the future. Let's give a warm welcome to our speaker. One more thing, if anyone wants to join us for dinner with the speaker tonight at Hetzel at 6, please talk to me. Then I will make sure there is a room on the table for you.
Yes.
Okay, thank you very much, and thanks for inviting me here. It's been a very interesting morning talking about planets, which is not something I normally do. But I will try to point out a little bit about the planets and these new missions and how that will affect what you are doing here. But this is actually a picture of the Gaia mission. I've just tinted it red to give you the impression of the GaiaNIR mission. And the important point to note is Gaia has two telescopes. One is coming out here, and the other is coming out the other side. And basically, they're collecting light from two widely separated points on the sky, and that's very important for doing the astrometry. So it always has to have at least two telescopes. So when I started this work in 2007, this was one of the first view graphs that people showed me. So it's quite an old graph, not made by me, I think maybe by Michael Perryman. And basically, the idea of this graph was to get across the idea about Gaia, and I'm going to talk about Gaia now for a while and explain how this astrometry works. Is that Gaia type of astrometry basically touches on almost all areas of astrophysics. So things like galactic structure are very important, of course, because it measures all the stars, and the motion of the stars tell us about the galaxy and how it works. But it also gives stellar physics through color HR diagrams. It can look at binary stellar systems, and it can also look at, of course, exoplanets, because the stars wobble when there's a planet orbiting them. And that's something that's very interesting. But we also have lots of noise in Gaia. Things like the solar system get in the way, and we actually measure all the asteroids just by accident, which turns out to be a rather useful little thing to have. But Gaia is also, though, a service mission. It provides a service to the astronomical community. And part of that comes from things like defining a celestial reference frame in the optical, which is now being published, at least the preliminary versions of it. And it can also do fundamental physics, like measuring proper motion. It can test general relativity, and it can also measure the acceleration of the solar system towards the galactic center via proper motion patterns. And of course, it sees galaxies and quasars also, and they're often detected as point-like objects, so we can actually get the motions of objects outside of our galaxy, and I will come back to that a little bit later. GaiaNIR, of course, is meant to be very similar. The difference, of course, is that NIR, near infrared. So by pushing into the near infrared, we're able to access the central parts of the galaxy. And that's where all the really dynamical action goes on in the galaxy. And that's why we want to go into infrared. But it can also allow us to look into clusters and so on and see what's going on inside of star-forming regions. So that's something that people here are interested in. But of course, if we want to get GaiaNIR accepted, we have to increase the science return by basically an order of magnitude in many different areas. So in terms of the number of stars, the importance of the scientific regions we're looking at, and also in terms of the accuracy that we can actually achieve. So that's quite a big challenge. And if we do that, then we can make a beautiful mission. So I'll introduce here the spacecraft again very quickly. But as I said already, it has 2 telescopes. These telescopes form 2 fields of view, widely separated on the sky, and they focus the light through a series of ping-ponging mirrors, basically 6 mirrors, onto a single focal plane. And that means on the focal plane, we actually get 2 pictures of different patches of the sky at the same time, and we have to disentangle those 2 pictures to figure out what part of the sky they're actually. This is the main astrometric field, this big gray patch here. It's where we get our measurements for astrometry. And astrometry measurements are basically transit times. We measure the time at which a star crosses an imaginary line on these detectors, and we get timing measurements. And if we know where the satellite is pointing at that time, then we know where on the sky the star is. That's the basic idea. But we also have a blue photometer and a red photometer to get the color information of the star. It also gives low dispersion spectrum also of the stars. And we also have a radial velocity spectrometer on board to get the 6th astrometric parameter, which is the radial motion of the stars, which we do not get from astrometry directly in the general case. So the stars move across the focal plane, and small windows are centered on each object, and it's those small windows that are actually transmitted to ground. The rest of the information we throw away, the background information. And the stars that are too faint then don't get detected in this process. So how does astrometry work? Now, the traditional way astrometry works is the one that you've probably learnt in your basic courses. Basically, we have the sun here and we have the Earth at, say, in June, and the Earth, of course, goes around and it's on the other side of the sun in December. And using that, then, if we look at a nearby star, we can see that the angle of that star with respect to distant background stars changes. So in June, the star appears to be here, whereas in December, the star appears to have shifted. And this is what we can do to measure this parallax angle here, which is called P here. And the problem with this method, of course, is that these distant background stars, they're actually moving as well. So you can't really use this method. It only works to a certain level of approximation. And it's not the best way to map the sky and get a complete overview of the entire sky. Now, Gaia is very different. And this is the reason that we have 2 fields on Gaia. Here's the Gaia spacecraft. This is its spin axis. And the spin axis is held at 45 degrees to the sun. Now, a parallax shift in this diagram means that we get a shift of the star on a great circle towards the sun, basically. That's what a parallax measurement translates into. And Gaia has a very special arrangement. What we actually measure on Gaia is the projection of this vector onto the scanning circle, which is this great circle here. And you can see here for star 1, its projection onto the scanning circle gives a finite value. But for star 2, a special arrangement happens to be shown here, where the projection of this star onto the scanning circle basically gives 0. And that means that star 1 is independent, or in other words, it gives an absolute parallax. Now, this is a special kind of geometry that occurs all the time as we're taking measurements with different stars, but every star has at least one of these cases. And when we put these into a global solution for the whole mission, it means that the entire mission has to be consistent with these measurements. And that means that all the parameters we get for all of the stars are absolute parallaxes. And this is one of the special ways of doing space astrometry that's very unique to Gaia and can't be done from ground. Just to give you an idea about the scanning law, how we scan the sky, you can see here that Gaia, as it scans the skies, it rotates every 6 hours. So it does a great circle every 6 hours, but at the same time, the spin axis precesses. And that means that these scanning circles span out. And this is another diagram showing it over a longer period of time. If I show you a video of this, here we have one of the fields of view, and here we have another field of view. And the blue line here is the ecliptic plane, and there's the sun, and I think this is the spin axis here. And if I just play that video, you can see how Gaia scans the sky over a 5-year period. This is for. So you will see the video now playing. You can see the great circles are scanned out on the sky, and the precession of the spin axis, which is occurring here, causes these to shift ever so slightly every time we do a new scan of the sky. And then the video speeds up, and you can see how we now start to map the entire sky. And in a few seconds, it'll go even faster, so we can get up to 5 years and not have to wait a very long time. But you can see that we get more or less uniform coverage of the sky. In some regions of the sky, it's more dense than others, but as long as we have sufficient observations in every patch of the sky, then we eventually get a complete map of the sky. So I think we're up to 3-4 years now. And essentially, this was actually a simulation we developed in Lund many years ago, showing how we do this. Now you can see the results in Gaia Data Release 1 in 2016. We released a catalogue of 1.1 billion stars. And this contained only 14 months of data from Gaia. And you can see artifacts of the scanning law are still visible in the sky map. This is a density plot, by the way, and it shows various constellations here, galaxies, open clusters, and globular clusters. You can see the Magellanic Clouds, for example, which show up very beautifully in this. So you can see that Gaia does a lot of work. You can see the dust bands, which of course are the difficult bits because we can't see what's behind them in the galactic plane. And we also get the motions of these clusters and so on, which is also quite important for our science. In 2018, we released the second catalogue. Again, it's exactly the same map. It's a density map, but now there's color information is superimposed on the density map. You can see now it looks like a photograph. It's not a photograph, of course. It's a collection of all the data. And remember, we can zoom in on any patch of this map, and we can go deep into it and see all of the stars, and we have all of the astrometric data. That means positions, parallaxes, and proper motions, but we don't generally have the radial velocity, which is the 6th parameter. So that was 22 months of data, and you can see the solution clearly gets better all of the time. And then if we go to Gaia Data Release 3, which happened over 2020 and 22, we end up with 1.8 billion stars made up of 34 months of data. And of course, there's going to be future releases as well. There's going to be DR4 next year in late 2026. Where we're going to have 5 years worth of data, and then around 2030 we're going to release the final data catalogue, and that will consist of about 10 years of data. So these results are going to get much better, and you can see here immediately why we think we need to go into the near infrared, because all of these dusty patches here are obscuring the galaxy from our view in the optical. And that makes it very difficult, because this is where all the important stuff happens in the galaxy, basically, in terms of dynamics. So Gaia is a great mission. I'm going to bash it a little bit here because I think we can do much better than Gaia in the future. Here's a little video showing what the proper motions look like. This is the proper motions of 40,000 stars within 100 parsecs. And we show the change in their position over the coming 80,000 years. And if I just play that video, you can see how the stars move. And we limit the numbers because otherwise you would not see anything at all. The video plays very badly here. It's nice and smooth on my screen. It's a bit jumpy on the screen here. But you get the idea that the stars are moving. And we have the detailed numbers for every star in the catalogue of this 1 point. No, we have for 1.5 billion, we have all of the parameters, but that will improve with every release, and we will fill in the missing numbers with time. So you can see here that we can do a lot with dynamics in the galaxy. That's only the first 100 parsecs. So it's not very many stars, but also you get a lot of different science returns. Here you can make maps of the dust in the galaxy, for example, using the interstellar medium to reveal the interstellar dust. We can also make chemical maps because we have spectra, and they're very low resolution spectra. But we can actually use that to make chemical maps of the galaxy. And here you can see that there's a lot more metallicity, for example, around the galactic plane. And also we can do radial velocity measurements. So you have to think about what this shows you, but the dark color shows you that the galaxy is moving towards you, and the bright patches indicate that the galaxy is moving away from you. And you have to think about this because when the galaxy is at, if you look 90 degrees away from the galactic center, then the stars change direction every 90 degrees, basically. It's also a little bit more complicated to explain this diagram because it also includes our own stars motion. So you have to, in principle, subtract out our own motion as well. And then a similar diagram here is the velocity field of the tangential components. So you can see the scientific return is very important from this. This is a summary slide that ESA made up for the 1.8 billion stars showing what we have. I'll only comment on a few things here. From the color photometers, we get very low resolution spectra also, which turn out to be very useful for scientific purposes. And that gives information about the astrophysical parameters of the stars. We also have from the radial velocity spectrometer, we also get spectrum of the stars, and we can extract astrophysical properties from those also. The full astrometry we have for 1.5 billion stars at the moment, but as I say, that will increase. But look at the difference here with radial velocities that we measure from the spectrometer, we only get 33 million. And here, I think that's a terrible shame. I think radial velocities is something we can and must radically improve. So if we can do that with the near-infrared mission, that on its own would be a very important science case to get. And of course, Gaia can detect binary systems as well. It can do this by fitting Keplerian orbits, for example, to the objects, or it can just detect accelerations of stars. So the basic model is a linear model, but if we have a deviation from linear motion on the sky, we know that that's usually indicating a binary system of some sort. So Gaia, as you said, it was shut down actually on the 15th of January. And it collected 3 billion observations in total. So after 10 years of observing, or 10.5 to be exact. And here's some of the data numbers that are just show that, well, it collected a lot of data. And in Lund, we contributed a lot to the data processing of this basic data. So we developed a lot of the algorithms for converting this basic transit timing measurements into actual scientific data that can be used. So keep an eye on time. Here's a nice little video, and I'll just let this play because I think it's an animation, right? So it doesn't show the truth because Gaia actually only measures close to us in the galaxy. It doesn't measure this far side of the galaxy very well, but using symmetry arguments and small samples of very bright stars, one can infer the whole galaxy to make the full animation. And I think I have to...
This is our galaxy.
No, it doesn't play.
No space.
Turn down the volume.
The jury is like.
Yeah, then it goes off. Okay, we have to test that. Sorry, no, we didn't test this. So, but here are the maps that I showed earlier.
And this new animation is based on galaxies.
So this animation, I'll turn this down, but this animation is very nice, but of course it's not the truth, right? This is inferred from what we know, and it's also including lots of information. This asymmetry or warp in the galaxy is actually taken from the real data just by analyzing the data that we have. So people have used the real numbers to construct this nice image. But we should also note, when we look at the galaxy, you can see that most of the interesting regions are full of dust and gas in between the spiral arms and so on. We have all of this obscuration and star-forming regions, but especially towards the bulge and bar regions of the galaxy. This is the dynamical heart of the galaxy, and this is what astrometry really aims to do. And you can see that nicely illustrated here, all of these dusty bar, spiral bar regions here that are really obscuring it. And this is where we live and where we get our most accurate measurements. And of course, the problem in doing these measurements, people ask me, for example, how many spiral arms there are and how easy it is to infer them. But this is actually a very difficult problem because you don't get a complete sample of stars once you go out further. And trying to figure out what these overdensities are is actually extremely difficult. So trying to infer all of this information is very, very challenging. Oops. Move that. Do that instead. Yes, no, done that. Okay. So now I've talked a little bit about Gaia and explained what Gaia is really doing and how it is. But the challenge for us is that if we go into the infrared, what can we improve by doing this? How many stars can we detect? And how accurately can we do it in the galactic plane to see through all of this dust and gas that's in the disk of the galaxy? So we came up with initially we came up with three main science cases, which we put into this Voyage 2050 call from ESA for new proposals or teams for the future missions. And the first, obviously, is to add near-infrared astrometry and photometry to probe these dynamically important regions of the galaxy that are currently hidden to Gaia, simply because Gaia can't see deep into it. And we estimated from models of the galaxy that we would see about 15 billion stars. Now, this is to be compared to about 2 billion stars that we're going to have in the Gaia catalog. So this is a significant improvement in the number of objects that we can actually detect. And to do that, we would have to have a K-band cut off at about 2.5 microns in order to be able to detect that number. But another major science case is that for the 2.5 billion common stars, and you can see here I'm increasing the number of stars that Gaia is going to give us. And the reason I know this is that because we published accidentally that we've processed 2.5 billion observations of objects. And that means that in future catalogs, those observations are going to translate into catalog entries, I would predict. So that means that in the end, Gaia will probably have something like 2.5 billion stars. And if we were to combine those stars with a 20-year time gap between them, that would give us a total baseline given two 10-year missions of 40 years, basically. And that very long baseline in time would allow the proper motions of the stars to be significantly improved. And it's about 15 times better than we currently have with Gaia. So that's more than an order of magnitude improvement in the proper motions. But this is only done for the common stars between Gaia and the GaiaNIR mission. And of course, the GaiaNIR mission on its own with the other 12.5 billion stars that are new, then we will get similar accuracy to Gaia. So this is pretty impressive. The Gaia optical reference frame and catalog will actually decay over time. So if we don't redo the Gaia measurements over a period of time of about 50 years, then that catalog will become not useless, but much less useful. And it's very important that we refresh the catalog and then the catalog will remain accurate for a very, very long time. But we can also expand the optical reference frame to the near infrared. And if you think about modern telescopes, many modern telescopes have infrared instruments on board. And having a reference frame for those measurements that those other telescopes are doing is also a very important addition. Now, since making this proposal in Voyage 2050, we've also reconsidered what else we could add into the proposal. And of course, adding a radial velocity spectrometer on board would also be a very big improvement to actually do. And the idea here is that we want to aim for instead of getting 33 million radial velocities as we have with Gaia, we want to actually get radial velocities for vast numbers of objects. So we want to aim for something like 1 billion objects. And if, for example, we discussed that this morning about clusters and so on in star-forming regions, if you can get the other component, the missing component, which is radial velocity, then you can vastly improve the science return when studying these obscured regions. And that could be very important in the future. So I have here a very long list of science cases for each of these different main areas. I'm not going to go through all of these, but I want to pick out some things that are very important for near-infrared astrometry. And you can see, of course, exoplanets in dusty and star-forming regions is one of the important cases that people here in this audience might be interested in. We can see into the dusty star-forming regions and therefore detect exoplanets in those regions also, which Gaia probably can't do. We can also study the internal and bulk dynamics of young clusters, for example, where you have star formation. And there's many other obvious science cases here, and things like probing dark matter and so on. I won't go through all of these, but the point about this near-infrared astrometry, this you will get for basically 12.5 billion new stars in the new kind of GaiaNIR catalog. And that is an order of magnitude improvement in the number of objects that we can actually detect. So remember that Gaia surveys about 1% of the galaxy. We want to push this number up towards about 10% of the galaxy. So when I talk about the improved accuracy, improved accuracy is also important. So for these common stars, the 2.5 billion common stars between Gaia and GaiaNIR, you can do things like detecting exoplanets and binaries with periods of up to 40 years, because detection and determination of the orbital parameters of companions requires that you have a very long baseline to take the measurements over. So if you have a baseline of 40 years, that means you can detect the parameters of these binaries and exoplanets with periods of up to about 40 years. You can do, of course, a little bit better for some objects, but that means that things like Saturn-like planets would come into vogue. Gaia is able to measure exoplanets that are Jupiter and Saturn-like. It can't see very close in planets that have very short periods, just because of the cadence of its measurements. So that's one of the important science cases here. Just to show you how this is supposed to play out, if you do a simple postage stamp calculation, if you plug in the accuracies that we currently have today for Gaia into this equation, then you can work out what the improvement in accuracy will be. And so I've done that. I've plugged in the numbers into these equations, and you can see that you get accuracies in proper motions of the order of about 0.6 microarc seconds per year. That's into the nanoarc second regime. So that's where we get the improvement in accuracy. This is, as I said earlier, is about of the order of 15 times better than Gaia can do, but only in the proper motions. We also get improvements for parallaxes and positions, but that improvement is smaller. It's a factor of 1.4 roughly. But this is very important because there's a lot of objects in the galaxy. For example, if you think about stellar streams around the galaxy and so on, they're at the very limit of the detection of Gaia, and their proper motion accuracy is actually quite poor. And if we want to study things like dark matter, we have to radically improve the proper motion accuracy of those very faint objects. So by using this combination of having a mission of Gaia between 2015 and 2025, and then a second mission, the GaiaNIR mission from 2045 to 2055, then we can get this very long baseline and make the proper motions extremely accurate. Of course, we will retire, most of us, before this happens. So our main task actually is to hand over to the next generation of astrometers so that they can actually fulfill this mission. Another point to note is that Euclid, Roman, and Jasmine, a Japanese mission, will all fly sometime in the next 5 years. And that they can also be included in this catalog because they actually give first epoch measurements as well. So this is a nice way of bringing in multi-messenger science into the whole project. Because the measurements being made by Euclid and Roman are extremely complementary. They provide basically astrometry. They're doing very accurate measurements. It's up to us to process them. It's not their main mission to do astrometry, but we can include all of these measurements together with Gaia and also with GaiaNIR to make a very complete catalog and get very long baselines for many new objects. So the reference frame I've said already, but this, I'll be very quick on this, but you can see how the reference frame decays as we go forward in time. Sorry, this is the catalog aging here. The proper motion errors cause an increase in the positional uncertainty of the stars as we go forward in times. And likewise, if we want to propagate backwards in time. So this is for Gaia on its own, but if you combine Gaia and GaiaNIR together, you can see the scale here on the axis decreases by almost 2 orders of magnitude. And it means that the catalog will remain relevant and accurate for very long times into the future, like hundreds of years into the future. So that's another important point about combining the data together. So there's a view of the current reference frame from Gaia Data Release 3. These are the quasars that are used to define the optical ICRF tree. That's aligned with the normal radio ICRF. And you can see this gap in the center along the galactic plane. We're missing quasars, of course, because we can't see through the dust of the plane. And the idea that an infrared mission would help to vastly fill this in. And this is very important because then you have reference quasars in the galactic plane also. You can see here we only have a very small number of them at the moment. So people ask a lot about what's the big science question. I think these pictures, both of them are from Hubble. One is a visible picture from Hubble, and the other is a near-infrared picture from Hubble. And they're equivalent roughly to Gaia and GaiaNIR, comparing what the change in what you see, basically. You've probably seen these pictures before of the pillars of creation. Here you can see all the dust and gas. And you don't see many stars in the background because of this. But if you switch into the near-infrared using similar detectors to the ones that we would use on GaiaNIR, you can see that thousands of stars suddenly become visible. And that gets across this message that we can measure many, many more objects by going into the near-infrared. And there's some key science cases, and I think the most important ones lie in the bulge, the bar, and the disk regions, where all of this is obscured basically to Gaia, but yet it's a super important dynamical part of the galaxy. But other nice things are galactic streams can be used to probe the dark matter halo around the galaxy. And we can also look at proper motions in clusters that can also probe their dark matter halos. And there's also this nice discussion that's going on about intermediate mass black holes, of course, in globular clusters. But one of the challenges with globular clusters is that they're extremely dense and crowding occurs, and it's very hard to disentangle with a finite-sized telescope. We don't have the resolution to get in there well, but if we have very accurate proper motions around the globular clusters, we may be able to detect hints of these black holes lying inside of them. So GaiaNIR aims to answer very big questions in astronomy and also in many big areas of astronomy. And one that you people might be more interested in is the long period binaries and exoplanets. And basically, GaiaNIR would be able to help to fill in the population of solar system analogs that could be seen. So I'll move on to some detailed design parts of the mission here. In 2017, ESA did a CDF study, which is basically they put together a lot of scientists and engineers in a room, and they sit down and design the whole space mission from beginning to the end. And I was the science advisor for this. And at that time, our main objective was to try to keep GaiaNIR as a medium class mission. So with a budget below 600-700 million euros. And we came up with a design that was simpler than Gaia's design, and it ended up having one primary mirror and then with 2 flat folding mirrors at the entrance pupils to form the 2 different mirrors. And this design would work out basically quite a bit cheaper in order to fit into an M-class mission. However, this study actually found that GaiaNIR would still not fit in an M-class mission. Making this big torus, launching it, and so on, still turned out to be a large class mission. So we don't think we can do this as a medium class mission, at least at the moment. So this design was good, but I think we can do a little bit better. So I've been sitting down looking at this design, and one thing I think is that these flat mirrors actually reduce the number of photons by a factor of 2 that you collect. So going back to a Gaia design where we have 2 primary mirrors would actually be much better. But another idea, in order to increase the resolution, as we go into the infrared, we lose resolution. But one way to recover that is to use segmented mirrors. So a new design, I've come up with two new designs, actually. One is which we have two primary mirrors. And the other is a big design, what I call the large design, is where we introduce segmented mirrors. And each of these segments could be 1.7 meters long, which means that the diameter of the mirrors would be about 3.4 meters. And that would recover the resolution that we have in Gaia in the optical and make the mission very equivalent. And this is also important because it collects a lot more photons. So we've taken this design and use it quite a bit in our studies. So the detectors that we're planning to use are from Leonardo in the UK. Leonardo is an Italian company, but they bought up a small company in the UK that make avalanche photodiodes. And these avalanche photodiodes, they're basically like photomultiplier tubes. So one photon comes in and it generates 100 electrons through an avalanche process. And this is very important because these new detectors have very low read noise, which is one of the limiting factors that we have with Gaia. Gaia has very high read noise when you go to faint stars, and that actually limits the accuracy quite significantly that we can get. But in order to make this work, we have to have high frequency readout in these detectors, and they have such devices that can do high frequency readout, but they need to be developed a little bit more. And if we can do that, then we can integrate the light by sampling at very high frequencies and then stacking the images together, which is one of the challenges that we had with the detectors. These detectors can go up to 3.5 microns, but we think that 2.5 microns is good enough. One of the problems is going further into the infrared is that you actually get thermal noise, and that would actually degrade the measurement. So we think we're better off sticking to about 2.5 microns as the maximum wavelength. And the minimum wavelength is 800 nanometers. So it's enough overlap with Gaia in order that we can do these common solutions with Gaia as well. So these studies are ongoing in the UK, and we're going to pursue them a lot more now. Leonardo are developing their production of this type of detector quite a bit for ESA. So the focal plane of GaiaNIR is very similar. Here's the focal plane of Gaia on the left, which I showed you earlier. But the focal plane for GaiaNIR is very similar. We have an astrometric field here, but one of the differences is that we're going to superimpose filters directly on the astrometric field. And the reason for doing that is that you get very clean colors then, and the processing on determination of colors is very simple. And this can be done very easily by depositing filter material directly on the detectors. However, in Gaia, it was shown that basically these dispersion photometers were actually very useful, not for their intended determination of color, but also because of their, they produce very low resolution spectra, and that actually gives a lot of astrophysical information. So we decided that we would like to keep these dispersion photometers here to get low resolution astrophysical information for most of the stars. And we've also included a radial velocity spectrometer, and we're currently studying that to find out what kind of spectral lines we would like to use to determine radial velocities. But we would probably do something like apogee to do that. We're using apogee as a guide for what kind of spectra. So this is something that we're studying at the moment, and something that we want to develop a lot, because it's very important. If we could add this radial velocity spectrometer and we could go much deeper than Gaia did with its spectra, then we would be able to produce an outstanding mission that would really help us in the future. So what I've been doing recently in Lund, I've been doing a lot of end of mission accuracy calculations, basically. So we want to work out what is the error we would get with this instrument if we take a few different models and try them out. And these, what I've chosen for these models, I've chosen a medium-sized design, which is very like Gaia's, with a 1.7 meter diameter primary mirrors. And then I've taken a large design with 3.4 meter diameter large mirrors. In reality, we're probably going to have to settle for something in between because the large design is probably going to be very expensive and we're not sure we can afford it. So we have to do that. But basically what I can do is I can get the flux of various stellar types. And then I can feed them into these calculations and then work out the parallax uncertainty and also the proper motion uncertainty that we would have in the final catalogue. And these same calculations were done for Gaia also, so we could verify that the calculations actually worked. So on the left, I have the results for Gaia, and this follows a very standard pattern, if you know Gaia results, that as a function of magnitude, the errors increase dramatically. And because this is a simulation, I can go beyond the limiting magnitude of Gaia. And you can see that the errors in Gaia increase exponentially as you go to fainter and fainter magnitudes. And that's why the stars that are very faint in the catalogue might have milli-arcsecond errors instead of micro-arcsecond errors. And remember that most stars are faint. And that means that most stars sit down at this end in any catalogue. So it's very important that we improve the accuracy of the results down at the faint end of the catalogue. Now, I do the same calculation up to the 24th magnitude for GaiaNIR. On the left here, I have what I call this medium design. This is the 1.7 meter mirrors. And on the right-hand side, then I have the large design with the 3.4 meter mirrors. And you can see that the accuracy of the new curves is substantially lower. At 21st magnitude, it's only 58 microarcseconds. This is for a very heavily extinction M33 star. For Gaia, for the same star, it was 685 microarcseconds. That's a huge improvement, even for the medium design. And then if we go to the large design, that error comes down to about 27 microarcseconds. That's incredible accuracy that we didn't even imagine would be possible with Gaia, which is up there at 600. So it's a huge improvement in the accuracy if we can do this. You might wonder why the accuracy of the new mission is so much higher. And the reason here is, you can see here, this almost linear dependence of the increase in the errors. This is on a logarithmic scale, so it's really logarithmic increase. And you can see this linear behavior here. The main reason for this is the read noise of the detectors. These avalanche photodiodes have very low read noise, and this is a game changer in astronomy. If we can get these detectors to really work, and they already have large scale ones for conventional astronomy, their read noise is so low that we can really go to very faint magnitudes. And this will help greatly with the spectroscopic measurements as well. Because for getting radial velocities, having this low read noise means that we can go down to much lower, much fainter stars than Gaia. Gaia only goes down to 14th magnitude for radial velocities. So we could push this down to 16th, 17th magnitude maybe. We have to do some more studies on that, but this is what allows us to go down to very faint magnitudes. Now I can do the same calculations for the proper motions. These are the proper motions from GaiaNIR alone on the right-hand side. Again, for the medium and the large optics on GaiaNIR. And the top panels are all for a 5-year mission and the bottom panels for a 10-year mission. And again, I have the equivalent results for Gaia. And you can see if we just take the bottom panel here and we compare, we can see that only for blue stars does it do actually worse than Gaia. For all other stars, it does significantly better. For solar type stars, which is the yellow curve here, it's about equivalent to Gaia. But for red stars, different types of red stars here are shown. You can see that it does significantly better than Gaia because of this linear increase in the errors. So this is very important and shows that the proper motions can be improved dramatically for GaiaNIR on its own. But if we also take the combined solution, I said that for 2.5 billion stars, we could do combined solutions. Now you can see that the scale on the axis, sorry, I'm somehow on the wrong result. This is the one I want. If I combine the common proper motions for these 2.5 billion stars, you can see the axes now have dropped by an order of magnitude. It's 10 to the 3 now, so that's a milliarc second. It was 10 to the power of 4 in the previous plots. So that means that we get an order of magnitude improvement. And you can see even for the GaiaNIR medium-sized design, the results are outstanding compared to Gaia. I think it's more obvious maybe in the single measurements here. The interesting thing about the combined accuracy is that it's the mission with the lowest accuracy that dominates. So Gaia is actually limiting the improvement here because Gaia is less accurate. And that's interesting. And this is one of the reasons when we produced the first catalog from Gaia, we included Hipparchus information and the Tuka2 catalog, but that actually limited the overall accuracy of the combined catalog because Hipparchus was less accurate, basically. So then for subsequent releases, for data release 2 and 3, we got rid of Hipparchus, basically, because it would degrade the results. And something true is happening here as well. We can't, for the combined mission, we can't go that much beyond Gaia, because Gaia is the limiting factor in this case. The new mission is actually doing better on its own in the relative sense. So I'll try to finish up now and take some questions. But the main reason that we get a better astrometric performance for the new mission is the new avalanche photodiode detectors. They're really quite outstanding. We've done other things, of course, as well to optimize the mission. We've optimized the scanning law. We can do things like changing the sun aspect angle, and we can change the scan rate as well if we want to go deeper to get better radial velocities. We have a proposal for doing that. But also the fact that we're going to longer wavelengths when we go into the infrared generally makes astrometry worse because the accuracy depends on the wavelength as well. But the fact that we have roughly three times the bandwidth in that we're sampling in terms of wavelength, that actually compensates for going to the longer wavelengths. And that means we can still do an extremely accurate mission, which wasn't actually, to a lot of people, that wasn't obvious when we started out on this. But the real improvement comes from the lower read noise and the lower background noise in the new detectors, which is a real game changer. So we don't want to go to longer wavelengths than 2.5 microns. We think it's actually better to go deeper than Gaia and get more stars. So the numbers I'm giving you here are for an equivalent depth to Gaia. If we go deeper in parts of the galaxy, at least, we can go deeper. If we in the galactic center, if we try to go deeper, we end up with crowding issues, and it's going to be quite difficult to get deeper than Gaia. But we have the option of going to 23rd or 24th magnitude with these new detectors. And that means that this number I'm claiming of 15 billion stars is actually a minimum value. It could be significantly larger depending on the depth that we actually choose in the end. And we have to figure out how deep we really want to go.
K magnitudes, yeah? K?
No, this is actually in G magnitude. We can convert to K magnitude as well, but it's about 1 magnitude different. I keep forgetting the direction. But yeah, if you talk about infrared, everybody wants it in H or K magnitude, and it gets quite confusing. To have the comparison with Gaia, I want to keep it in G magnitude, but we can convert to 2. This idea of using segmented mirrors would give us an outstanding mission. The problem with adding 2 segmented mirrors instead of 1 single mirror is that we increase the weight significantly. We also have to increase the radius of the torus significantly, which means a bigger launch spacecraft. So it's very unclear to me if we can afford to do this or not. And I think we need a new cost study basically to find out how big we could make those mirrors. So the maximum is probably 3.4, but in reality, we will probably have to settle for something smaller. The optics people I've spoken to didn't really think there would be a big problem in using segmented mirrors. It's not like James Webb where you would have to unfold everything. These could be put in place at launch and then just fine-tuned after launch. So it would be a very simple mechanism. So all you have to do is cope with the bigger mass, basically. But that costs a lot of money in space. But on the other hand, launchers are cheaper and bigger now as well. So maybe it's possible to do this and collect more photons. Which would be very, very good. The combination of these improvements then results in a mission basically that can outperform Gaia, which to me was surprising, and I think to other people was surprising as well. Until we did these studies, you can significantly outperform Gaia if you do it this way. And I think a real killer science case, if we can get a spectrograph and maybe at a slower scan rate in order to collect more photons, it means we could go significantly deeper and go really for massive numbers of radial velocities. And that's something that's really needed for all kinds of dynamical studies. If we had more radial velocities, we have the full 6-dimensional phase space. And that has many impacts on your science cases, for example, as well. It would be a really nice achievement to do that. So I think I'll stop there. I'm sorry I didn't talk about exoplanets too much because it's really a galactic mission, but we do get a lot of exoplanet science also out of this. Okay, thank you.
Any questions? Anyone else? Shall I start at the back?
Up to you. I'm just, did anybody try to estimate already from this wobble of the star positions, how many exoplanets could be detected this way?
Perryman did several studies of this over the years. So he's a number of papers on it. I think it was of the order of 20,000, if I remember correctly. They're all estimates, but I should say the exoplanet data from Gaia, it's coming out in like late next year. So what you need to do the exoplanet solutions is the time series of the Gaia measurements, and that hasn't been published yet. So this is going to be released together with software tools that you can do your own solutions.
So these 20,000, do you refer to those which are coming from Gaia?
They're the ones from Gaia. And
I mean near-infrared Gaia.
Near-infrared, we haven't estimated that yet, but I don't think it'll be massively more because most of these exoplanet systems are close to us and the amount of extinction is not massive, except in these clusters that you're studying. These star-forming regions. So we will get more, but I don't expect it'll be orders of magnitude more. It might be 25, 30,000 then.
So the limiting factor is the astrometry noise with a lower magnitude, higher magnitude. So that you lose the accuracy to say that to
yeah, exactly. I mean, yeah. But I think if these detectors really prove to be more accurate, it means we could go out further with the same accuracy, and then we might increase these catalogs. But
it's an interesting number. Sometimes you see this. You know, how many planets do you detect with a mission?
Yeah, it's an easy question to ask, but you have to base it on models though until we get the next release. But it's only a year and a half away. It's not very long to wait. So then we'll start to see what really comes out. Sorry.
Okay, thank you very much. So there's another thing that actually is impacting the planet science, which is the properties of the host star. So you said you can measure metallicity. Is first of all, what's the accuracy metallicity? How many decks you can get, and is the wave velocity helping in some respect that you get actually?
Yeah. I don't know the dex number, but the metallicity comes from the low dispersion spectra and from the higher resolution. So the resolution is about 11,000 on Gaia. And the spectrograph we would design would probably be similar. I don't know these numbers off the top of my head, but it's.
But would the spectrograph help as well in order to get better data?
Yeah, but the problem with the spectrograph is that it's going to have to be in a narrow bandwidth. Band range. So we're thinking of 100 nanometers or so in something around 1600 nanometers, because that's what Apogee did, and they did it for good reasons. There's lots of strong spectral lines in that region that could be used for radial velocities. So my primary aim is radial velocities, but of course, when you get a small spectrum, of course, you can get the chemical abundances as well, at least to some extent.
I believe there's some elements.
Yeah.
Okay, cool.
Thank you very much, David. When you designed Gaia at the beginning, machine learning and artificial intelligence, they were not okay.
No.
Now they are.
Yes.
Is there anything you would do different now as a result of that, both in the instrumentation but also in the consortium itself?
Yeah, I don't think the instrumentation we would change. I think the instrumentation part is very close to being the best we can come up with now. We could add, for example, a third telescope, but it would just add a lot of weight and expense, and it would be better, but not significantly, I think. But machine learning, yes, everybody's using it. It can be misused as well. So, but I mean, I think we have to think about how to handle large data sets now. And it's already evident in Gaia, and a lot of this wasn't in place, but you can see lots of now machine learning algorithms being used on Gaia data. And this has come from young people mostly in the community who haven't been involved in Gaia. And I think that's only going to get bigger. So in the data processing part for releasing the results, I think that the catalog we will release will still be the fundamental parameters, and I think it's still for the community to do the machine learning on the data sets. I think this has been deliberately done on Gaia. So even though by the time Gaia made its releases, machine learning was everywhere by then, people didn't want to bring that into the formal data processing. They wanted to leave that to the community. And that's why also the exoplanet time series, only a sample of exoplanets will be published from a small subset and very clear cases, but the rest of it will be left to the community as well. And there they can run their machine learning algorithms to see are there other exoplanets and so on. So I still think this will be a community-driven thing and not something the consortium should take over and do for everybody.
Even for infrared Gaia?
Even for infrared Gaia, yes. I think the community should do this part. Because the amount of processing you would have to do it for billions of objects would be so horrendously large. And yet we have a community of people who are dying to do this. So let the young people have fun with it. I think that's the correct approach. It's been used for Gaia, and I think it's very successful. And that's why Gaia has so many citations in the literature. It's because we leave a lot of the exciting science for the community, and we take only, you might argue we lose out a little bit the people who put all the effort into doing it, but this is the policy in ESA as well, to make it available to the community as soon as possible and not just grab all the science proprietary science cases for ourselves. So I mean, I think we get a lot out of Gaia anyway from the citations we get. So I think the mission is more popular when we give it away for free. Yeah, open source. It somehow works.
Two questions. First is, why the data release like 2 and 3 and not containing the entire number of stars? Do you have a threshold in which you don't have enough accuracy to say, okay, we keep these stars away? Because you have the data, right, from after.
No, well, Gaia only stopped, last month. So we couldn't really. It takes years to process the data, so we couldn't release that data straight away. It's going to be released in 2030.
But the entire sky has been scanned after 6 months already, right?
So you need a minimum kind of 12 months of data to get a complete scan of the sky. And so that's why the first data release had 14 months of data. And actually even then we couldn't get all the astrometric parameters. You needed kind of a longer baseline to get the parallax curves, basically, because the Earth's orbit is only 1 year, right?
Yeah.
So that's kind of a limiting factor. You have to have a certain long baseline. So with 22 months of data, that was the first time we could make an independent catalog, and we did that as quickly as we could then. So I think it came out about a year after the data was collected. And data release 3, then we processed as much data as we could, but we have to start like 2 or 3 years in advance to process the data and then to have it released. So it's quite a big amount of work. And so we've had access to data release 4 for a year or so already within the consortium, but we haven't released that yet because all the astrophysical parameters have to be processed as well. So to make the full release, we have to take much more time in order to get all of the parameters. And that's why we need another at least 5 years to get the final release out as well. It's simply manpower and computer power. There's a lot of processing going on.
You freeze the time where it's okay, this
Yeah.
data, we process it and now.
Yes, exactly. Yeah. So originally it was planned to have a cycle of every 6 months. That didn't really work in the end. It was too quick. But we have longer periods every few years. Then we freeze everything, make a release. And in the meantime, while things are being frozen, we're processing the next set of data as well at the same time.
And my second question is on the spin rate of the spacecraft. What dictates the speed at which it has to scan the sky? Because the slower you go, the more photon you can collect on the same, the star will be longer on the detector, right? And then you can have higher flux.
Yeah.
It is nice for higher magnitude.
Yeah, so this is a trade-off. I mean, you want to collect a certain amount of flux, but you also recognize that you're going to go through the galactic plane, and if you go too fast, you won't be able to collect enough. You'll have too many stars crossing the focal plane at the same time, which also consumes the telemetry budget. So there's all sorts of strange constraints that you might not think about to begin with. And then when you're out of the galactic plane, you could probably speed up the scan rate a little bit, but you don't want to have a changing scan rate all the time. That would make the processing very complicated. So it's kind of practical trade-offs between, going quickly and going how many measurements you get. I mean, if you're scanning the sky continuously, the total number of photons in the mission remains constant. It's only the number of photons per detector that changes if you change the scan rate. So I think it was a compromise of getting the scanning law of Gaia was studied for many years, and it was a compromise of getting good sky coverage, a number of scanning angles from different directions, and so on over the period of the mission. So I mean, you could pick different values. A factor of 2 or something different probably would work fine as well, but.
That would help for the readout noise issue, right?
Yeah, the readout noise issue could be improved if you scan slower, but then you would get fewer measurements in different directions. And remember, Gaia is a one-dimensional instrument. It makes its measurements in one direction. So if 2 stars are close together and you scan across them, you'll only see 1 star. And that's why you have to do a scan from a different direction at a later time to disentangle those stars that are overlapping. And so we get the 3-dimensional aspect by doing scans from different directions over time. And that allows us to disentangle the problem. So it was a compromise, and it could be changed a little bit. For radial velocities, I think we could have periods of a year where we'd scan slower to collect more photons for radial velocity measurements from each individual detector. And then you could speed up the scan rate as well to maintain a uniform scanning law. So we're looking at things like that to see if it's useful or not to do this. But it makes things more complicated if we do it.
Thank you very much. One more question, and I think it might be the last question of today. So David, we'll be here all afternoon. I do urge you all to lock on this door and talk soon. But yeah, one final question for this.
All right. Thanks a lot for the talk. Can you talk a bit more about this 10-year baseline? Because I imagine if you consider all the different science cases, you can optimize this to wide.
Yeah. So, yeah, I mean, so the Gaia's nominal mission was 5 years. And I think it had an extended for 1 year, so 6 years option. If you go to the space agency and say, I want a 10-year mission, then they will put much more stringent requirements on you. And so the idea is you propose a mission of 5 years, and ESA will always add a margin of fuel and so on. So you can basically get 10 years for free. And you have to, of course, justify why you need more time, of course, because it costs money to run the spacecraft. So that was the strategy that I don't think it was planned, but that's how it worked out in Gaia. There was enough fuel on board to last for 10 years, basically, and there were very good science cases to continue scanning for the 10 years. But then the fuel basically ran out in January of this year, so that's why it ended. It was actually 10.5 years, I think, it was in operation. It would be nice to continue on, but it becomes harder to justify the science because it becomes incremental at some level. Having a doubling the baseline is not incremental. That's a big improvement, but especially in proper motions, it's a factor of 2√2 by doubling the baseline, improvement in proper motions. But justifying it further would be harder and harder. So I think Gaia finished at the optimal time and, it did a good job. And we had no major problems, really, minor problems. But so it was a very fortunate mission. And so for GaiaNIR, we will also propose a 5-year nominal mission. But if we're lucky and we have an excess of fuel, we might get 10 years. But we will have to justify that as well. We won't just get it automatically.
Thank you once again. Thank you very much. It's a fantastic instrument. So like I said,